Hello, everyone. Let's start with this lecture. We study the time domain analysis module of discrete systems for signals and linear systems. We are starting part 5 today. Time domain analysis of discrete systems. The seventh part is the nature and application of convolution sum. First, let's analyze the properties of convolution sum. The first is convolution and coincidence exchange law. Second, convolution sum conform to the law of combination, which means that if the system is cascade, the equivalent unit sequence response corresponding to the cascade subsystem is the result of convolution of two subsystems. The third convolution sum conforms to the law of distribution. That means, if two subsystems are parallel, the equivalent unit sequence response of a parallel system is the sum of the unit sequence response of the two subsystems. The fourth arbitrary function and delta of k convolution is equal to any function itself. This content can be proved by the definition of convolution sum. For the same reason, f of k convolution delta of k minus 1 is equal to f of k minus 1. The corresponding expression is the same result of f of k delay. One more thing, suppose f1 of k convolution f2 of k is equal to f of k. Then, between f1 of k minus k1 convolution f2 of k minus k2 and the original sequence f of k, what relationship does it satisfy? So it does the same delay processing. It equals to f of k minus k1 minus k2. The corresponding properties of convolution sum general non-existence of calculus. What we focused on is the application of these properties of convolution sum. That is, using these properties in other projects or in practice. We can use the properties of convolution sum to solve some specific problems. We can use the properties of convolution sum to solve some specific problems. First of all, let's use the properties of convolution sum to find convolution sum. Given a composite system, this composite system is parallel with H1 and H2, and then it cascades with H1. The specific values of H1 of k and H2 of k have been given. It is required to find the unit sequence response h of k of this composite system. Then, according to the definition of convolution sum, our corresponding system has the form H1 and H2 in parallel, and then it cascades with H1. According to the combination law and the corresponding distribution law, we get, that is to say, H1 and H2 are parallel equivalent to these two subsystems. The form of the summation of the unit sequence response. So the same thing as the H1 cascade. is the same thing as this first composite system, convolved with the second h1 of k. Let's write this, and you can see it. h1 of k minus h2 of k and h1 of k as convolution sum. This is the unit sequence response of the equivalent composite system. It can be solved by the properties of the correlation. We take the value of the unit sequence response of the subsystem, bring it in and sort it out accordingly. So you can see that what we have got is a form like this, using related properties to find convolution sum. Let's take another concrete example. Specific values of fk and hk are known. Take the convolution of these two sequences. So, to find the convolution sum of these two sequences, we can see that f of k is equal to R3 of k. We expand it into the form of shift sequence expression of delta of k. Then the corresponding form of h of k, we also express it in the form of delta of k and its shift sequence. So that means f of k equals delta of k plus delta of k minus 1 plus delta of k minus 2. h of k equals to delta of k plus 2 delta of k minus 1 plus 3 delta of k minus 2. Then find the convolution sum of these two sequences. According to such a property of convolution of any sequence and delta of k, we can see that f of k convolution h of k is equal to this sequence convolves the result of this sequence. It is the result of convolution of delta of k and its shift sequence. We can see that the convolution of f of k and delta of k is equal to f of k itself, and then it convolutes with 2 times of delta of k minus 1 equal to f of k itself. I'm going to shift it to the right by 1. Convolution with 3 times of delta of k minus 2 is equal to f of k itself, moving 2 units to the right. So let's see. That's the result of the convolution. Finally, carry on the corresponding arrangement, so the collation result is a form like this. In this case, 1 is zero state response of the system equal to the convolution sum of excitation and unit sequence response. The second one is that convolution of any sequence and delta of k phase equals to any sequence itself. If there is a shift, then let's think about the shift up there. The application of convolution sum can also be used to solve the corresponding response. Now let's do a specific example. Given an LTI discrete system block diagram form as shown in the figure, the initial state is y of minus 1, y of minus 2 given. The question is to find the total response y of k of the system with given excitation f of k. So the first thing we need to do is to follow the block diagram. Write out the difference equation. We have talked about the column writing method before, so let's see. The result is a difference equation that looks like this. The first step is to get the full response. So let's start with the zero input response. Zero input response according to initial conditions. Let's iterate over it. Yzi of 0, yzi of 1 can be solved iteratively. After you iterate over these two initial values, we write the characteristic equation from the difference equation. The characteristic roots are two single roots. So the form of the zero input response, we have come to the conclusion that it's such a form. According to the yzi of 0, yzi of 1 just iterated, the initial value is substituted in. So the corresponding two coefficients, undetermined coefficient czi of 0, czi of 1 are worked out. Take it to the equation above. So the zero input response is what we are going to solve for. Now, let's solve for the zero-state response. Zero-state response solution. We use the form of convolution sum to solve the problem. Therefore, we need to follow the form of the block diagram first. The unit sequence response of the system is solved. This unit sequence response solution, you can refer to the next page. We will talk about that later. Let's write the result of the unit sequence here. So, according to the physical meaning of the sum of convolutions, we can get the zero-state response of the system equal to the result of convolution sum of unit sequence response and excitation. The result of the unit sequence response is here. The given incentives is a form of this. So take the convolution of these two. We get the zero-state response for the system. So the full response of the system equals to the sum of zero input and zero state. Let's look at the solution process of the unit sequence response h of k. So according to a differential equation like this, the initial condition is that h of -1 and h of -2 are equal to 0. The specific solution process is a form like this. After k goes to 0, the difference equation becomes a homogeneous difference equation. So its corresponding characteristic equation and its characteristic root don't change. It is still -1 and 2. So the form of the homogeneous solution is still a result of this. Once you get the result, we need to iterate by the initial conditions to get the iteration of h1 of 0 and h1 of 1 from 0 to 2 ones. Then take h1 of 0 and h1 of 1 into h1 of k. Two undetermined coefficients c1 and c2 are solved. So you can see that the specific value of the unit sequence response h1 of k has been solved. This is the system that we just gave. The process of finding the specific solution of h of k. So you can see that using convolution sum, the zero-state response of the system can be easily solved. This is a very important application of it. Thanks. That's all for today.